we have discussed the stationary non-degenerate perturbation theory in our previous lecture. And now, today we are going to see the stationary degenerate perturbation theory. You know, when you say that the system is, any energy eigenvalue of a system is non-degenerate, that means corresponding to that energy eigenvalue there is only one eigenstate. But when for a given energy eigenvalue there is two or more eigenstates or quantum states, then you said that energy eigenvalue is degenerated. If there are two eigenstates corresponding to an energy eigenvalue, the degeneracy is 2. And in general, if you consider that for a given energy eigenvalue there are f number of eigenstates, then that energy eigenvalue is called f whole degenerate. Okay? So if you now consider that the unperturbed Hamiltonian H naught of our system is not non-degenerate, but it is degenerated. So when H naught, which is actually the unperturbed Hamiltonian of our system, that is degenerate, then actually the time independent non-degenerate perturbation theory will fail. That cannot be applied. Because in that condition, if you will apply the non-degenerate theory of perturbation, but the unperturbed Hamiltonian is degenerate, and you are going to apply the theory, the expression for energy correction which you have obtained in your previous lecture for the case of non-degenerate system, then actually it is found that the result will get diverged, that will become infinite or undefined, because when you have seen the expression for the energy correction up to second order, particularly in second order energy correction expression, the term in the denominator becomes 0, and due to that 0 the energy correction term becomes either undefined or you can say infinite. Okay? And that's why we simply say that if the unperturbed Hamiltonian H naught is degenerate, then you can't apply the concept of perturbation theory which we have learnt in your previous lecture. Actually, in that condition, we have to see some another theory that is actually called the stationary degenerate perturbation theory. Okay? So how we can follow the stationary degenerate perturbation theory, what are its basic features, we are going to learn in this lecture. So now let us consider that applying this perturbation theory, we have to determine the energy spectrum and the eigenstate of a system whose unperturbed Hamiltonian is H naught. And this H naught is not non-degenerate, but it is degenerate. Then you know, whenever you have to solve a particular physical problem, first of all, we write the Schrödinger equation for that system. And if you consider that H is the Hamiltonian of our system and this kth psi n is its eigenstate or eigenvector or eigenfunction, then the eigenvalue equation of this system is written as h hat ket psi n equal to En ket psi n. Here actually En is the energy eigenvalue, you know. But as you have learnt in the previous lecture that in perturbation theory, we split this Hamiltonian h hat in two parts. The first part of h hat is h naught hat, which is called unperturbed Hamiltonian, or this is the Hamiltonian for which the Schrodinger equation can be exactly solved. Okay? And the second part is given by this HP, which is called actually perturbation term, and this HP is much smaller than this H naught. You have learned. So instead of this Hamiltonian H in perturbation theory, you may write H naught plus HP. Okay. Now, if you write the equation for the unperturbed Hamiltonian, in case of, let us say, the non-degenerate case, then you have written that this H naught hat operated on ket phi n, and that is equal to En0 ket phi n. You have written this equation in your previous lecture while discussing the stationary non-degenerate perturbation theory. Here you know this ket phi n actually represents the eigenfunction for the unperturbed Hamiltonian H naught. Okay? And in that case, actually corresponding to this energy eigenvalue En0, there is only one eigenfunction phi n. Okay? But here we are considering that this Hamiltonian H naught is not non-degenerate, but it is degenerate. So now let us consider that this energy level En0, which is the energy eigenvalue of this operator H naught, let us say that this is f-fold degenerate. What does it mean? When you say that this energy eigenvalue En0 or this energy level En0 is f-fold degenerate, it means for this value of En0 will have one and only one value. But corresponding to this same energy eigenvalue, there will be f eigenstates. And you can denote those f different eigenstates by the symbol ket phi n1, ket phi n2, so on, ket phi nf. Or in brief, you may write these eigenvectors as this ket phi n alpha, where alpha runs from 1 to f. Okay? So, if I will ask you that for the eigenvector ket phi n1, what is the energy eigenvalue? Answer is En0. Again I will ask you, what is the energy eigenvalue for the another eigenvector ket phi n2? Answer is again En0. And in the similar manner you can say, for any eigenstate between this phi n1 and phi nf, the energy eigenvalue is same, and that is En0. So this energy eigenstate En0 is called f-fold degenerate. Okay, f-fold degenerate. So if you will now write the Schrodinger equation or the eigenvalue equation for the unperturbed Hamiltonian H naught, when this H naught is actually is degenerate and degeneracy is equal to F, then we will write the eigenvalue equation in this manner: H naught operated on kate phi and alpha. Mark here, when the case was of non-degenerate state, then I have written this eigenfunction by phi n. But here I am writing it phi and alpha, where alpha runs from 1 to f. And this En0, this is the energy eigenvalue. Okay? And you know, as I have told you, that for each phi and alpha, energy eigenvalue is same, and that will be En0. Okay? Actually, in this equation, you know, when you write this equation, this alpha stands for one or more quantum numbers. You will see later on, okay? That may be a quantum number L, that may be quantum number M, that may be quantum number N, principal quantum number, orbital quantum number, or magnetic quantum number, okay? And the energy eigenvalue, this En0, are independent of alpha. It does not depend. Alpha will have different value. When you will take alpha equal to 1, then En0 will remain En0. When you will take alpha is equal to 2, En0 will remain En0. So you can say that this alpha actually stands for one or more quantum numbers, and the energy eigenvalues, this En0, is completely independent of alpha. Okay? Now actually, one of the most important basic feature of this stationary degenerate perturbation theory is that if you are talking about zeroth-order approximation, actually in zeroth-order approximation, you may express the eigenfunction, this kate psi n, as a linear combination in terms of this eigenvector kate phi and alpha. Okay? So this kate psi n can be expressed as the linear combination of these eigenvectors phi and alpha. When you say that this kate psi n can be expressed in zeroth approximation as a linear combination of these functions, it means you may write kate psi n equal to a1 times kate phi n1 plus a2 times kate phi n2 plus so on, plus af times kate phi nf. Actually here a1, a2, a3, so on, af are the coefficients. Okay? And this phi n1, phi n2, phi n3 and phi nf, these are the f eigenvectors or the eigenstate of the system corresponding to the same energy eigenvalue En0. Okay? Actually, this expression in brief or in compact form you may write in this way: kate psi n equal to summation over alpha from 1 to f a alpha times kate phi n alpha. Okay? When you will substitute alpha equal to 1, 2, 3, so on up to f, you will get this expression. Okay? Now, actually, considering this state, that is phi n alpha, to be orthonormal with respect to the level alpha, then you know if this state kate phi n alpha is orthonormal, then you know the scalar product of this phi n alpha with itself, that is phi n beta, is simply equal to delta alpha beta, which is called actually the Kronecker delta. I think you have a concrete idea of the Dirac bracket algebra, because I have already provided this in my previous lecture on quantum mechanics. Okay? And if you are lacking something in Dirac bracket algebra, you must watch those videos. Okay? So the scalar product of this phi and alpha with phi and beta, this is given by the Kronecker delta. This is called Kronecker delta. Okay? Delta alpha beta. And you know, this Kronecker delta is equal to 1 if alpha is equal to beta, but it is 0 if alpha is not equal to beta. So this scalar product will be equal to 1 when you will take alpha equal to beta, and this will be equal to 0 if you will take alpha is not equal to beta. Okay? And we also consider that the eigenfunction discrete psi n is normalized. And what is the condition for normalized wave function? The condition is the scalar product of this psi n with itself must be equal to 1. Must be equal to 1. When you say orthonormal, that means this eigenfunction will be orthogonal and normalized too. Okay? When alpha is different from beta, then the result is 0, which is the condition for orthogonality. And this 1 is the condition for normalized eigenfunction. Sorry. So, these are our consideration. We consider that this basis vector phi and alpha is orthonormal basis, and the eigenvector ket psi n is normalized, and so these two results will hold. Okay? Now, if you consider these two important facts, in that condition, now you can easily find the values of the coefficients A alpha. And for this, let us take the product of this equation 3 with bra psi n, or you can say take the product of equation 3 from left side with bra psi n. So you can see now when we will take the product of this equation 3 with bra psi n, then LHS will be this much. Okay? And in RHS you can see what will be your result. Here you have to take again the value of bra psi n, and when you will write bra psi n from here, you know bra psi n. You know bra psi n is simply the complex conjugate of ket psi n. So this will be summation, let us say beta equal to 1 to f. Okay? A beta a star. Okay? And a beta star, and this pi n beta. You can write this one. And when you will take the product of this with this, what will be that? That will be A alpha star times A beta. Here you can take A alpha star instead of A beta star. You may take. Okay? Alpha beta may be interchanged. And so inside this summation, there will be A alpha star times A beta star, and the remaining term will be what? The remaining term will be actually this much. That is the scalar product of phi n alpha with phi n beta, which is equal to this much. Here there is phi n alpha and here is phi n beta. Okay. So it has been written here. You may also write this as delta beta alpha, because here we are taking the product of phi n beta with phi n alpha, and this may be written as delta beta alpha. So instead of delta alpha beta, you may write this much. Okay. And if alpha is not equal to beta, then this will vanish and it will not give you the value of A alpha. So for getting the value of coefficients, you must take alpha equal to beta. And when you will take alpha equal to beta, this Kronecker delta will be 1. Okay. And then instead of beta, we will write alpha. And so this will be A alpha star times A alpha. And what is A alpha star times A alpha? This is simply a square of the modulus of A alpha. So instead of this taking alpha equal to beta, I have written summation alpha 1 to f, because now the beta is equal to alpha, so I have the limits is only for alpha, and mod of A alpha square. Okay, but that this product is equal to 1 because we consider that the eigenvector ket psi n is a normalized eigenvector. So this will be equal to 1. So in this way you can find the value of this A alpha. Okay, we can find it. Now in what follows we are going to show how to determine these coefficients and the first order correction to the energy. Okay, and for determining the coefficients and the first order energy correction, one thing here you should note that in the degenerate perturbation theory, we always talk about the first order energy correction, never higher order, because the higher order energy correction particularly gets diverged because in denominator there is 0. Okay, so whenever you apply the degenerate perturbation theory, always think regarding the determination of the first order energy correction. Okay, so now our aim is to determine the first order energy correction first of all, and then we will actually calculate the eigenvector 2. Okay, and for this what we will have to do, if your aim is to determine the first order energy correction and also to determine the coefficients A alpha, then you should substitute equation 2 and 3 in equation 1. You can see this is your equation 3, see here, and this is your equation number 2, and substitute these two equations here in equation 1. You can see this is H naught plus HP ket psi n, but ket psi n is defined here in this equation 3. So we will substitute the value of ket psi n from equation 3 in LHS and also in RHS. Okay, and for this H naught plus HP, H naught operated on this ket phi n alpha, we must write this. So using these two equations in one, what will be our result? Now you can see here. Actually in LHS you can see H naught plus HP operated on in fact ket psi n, and you have seen that ket psi n is equal to what? This is summation A alpha ket phi n alpha. This was your third equation. So instead of ket psi n, now I will write this much. Okay, and you have seen that this is En0 ket psi n. Okay, So this is En0 summation over alpha En0 k phi n alpha plus HP operated on k phi n alpha times A alpha, and that is equal to En times summation over alpha A alpha k phi n alpha. Now, for evaluating the energy correction term of first order, let us multiply this equation 5 by bra phi and beta. Bra, remember this system. So let us see. When you will take the product of this equation 5 with this bra phi and beta, what will be your result? You can see this will be summation over alpha, En0 is at age, and here we have to multiply this k phi and alpha with bra phi and beta from left. So this is the scalar product of phi and beta and phi and alpha. And plus here in second term there will be bra phi and beta h hat phi and alpha. Okay. Actually this is the expectation value of HP, you can see. Or you can say also that this is the matrix element and A alpha. And in RHS, again we will multiply by this bra phi and beta from left side. So now the RHS of equation 5 becomes like this. But you know that this scalar product of phi n beta and phi n alpha, this is equal to the Kronecker delta alpha beta, delta alpha beta. Or you may write delta beta alpha, you may write, there is no difference. The second term is at each, and this A alpha has been written earlier here. And again in RHS, this product is equal to the Kronecker delta. Okay. So your equation becomes like this. Okay. Now see, this equation may be written in this manner. Here, if you will take alpha is equal to beta, alpha equal to beta, it means you are now taking a particular value. In that condition, this first term will become what? This, not this first term, but the term in RHS, alpha and beta both are same, so this Kronecker delta will be 1, and instead of A alpha you may write A beta. So this is A beta En. Okay? And the first term in LHS, this will be A beta En0. Okay? And then you have to write this second term in LHS. This will be summation alpha 1 to f. A alpha is the multiplicative factor here. This is A alpha times this expression, this matrix element. Okay? Actually, this equation, which you have written here in equation number 7, you may write this equation in this manner. But what in this expression, this H hat P beta alpha denote, what this En1 denotes, now you can see. You know, En1, this is the first order energy correction. And the first order energy correction is actually equal to En1. This will be equal to En minus En0. Minus En0. That is actually the first order energy correction. Okay? So when you will take this term in LHS, then A beta will be common. Okay, and there will be En minus En0, and that is equal to actually En1. And this HP beta alpha, this is actually the matrix element which is defined in this manner. HP beta alpha, this is equal to this much. This is the matrix element. Okay. Actually, this equation number 8, you can see. This equation is f in a number. Okay. And so you can say that this is a system of f homogeneous linear equations for the coefficients a alpha. Okay. And these coefficients a alpha will have non-vanishing values, or these coefficients will be non-vanishing, non-zero, only when the determinant of its component of its multiples will vanish, will be zero. And you can see the determinant of the coefficient a multiple of the coefficient a alpha. This is determinant HP beta alpha minus En 1 delta alpha beta, that must be equal to 0. Now this is actually f by f determinant, and you can now write this determinant in expanded form in terms of its different elements. Okay. You know that actually here alpha and beta both runs from 1 to f. Beta and alpha both runs from 1 to f. So now this f by f determinant can be written as HP11, here alpha beta both are 1, minus En1. Mark it. And since you are taking alpha equal to 1, beta equal to 1, okay, therefore alpha is equal to beta, and that is equal to 1 in first term. And you know, when alpha and beta are equal, then Kronecker delta is 1. So at the place of delta alpha beta, I have written 1. So this is the first matrix element. Okay. Now let us take beta equal to 2. Alpha is fixed at 1 in first row. So when alpha is 1 but beta is 2, it means alpha is not equal to beta, then this Kronecker delta will be 0. And therefore, the second element of this determinant will be only HP12, because this delta alpha beta, that is delta 1 2, will be equal to 0, and therefore this second term will vanish. Similarly, the third term will be HP13. Here you can give the same argument, and the fth term is HP1F. Okay, HP1F. Similarly, in the second row, the different elements are HP21. Here, HP22. Since alpha is equal to beta, so Kronecker delta will be 1, and here there will be En minus 1. So in this way, you can write this f by f matrix, or you can say determinant, and this must be equal to 0 for the non-vanishing value of Al. Okay, non-vanishing value of A alpha. Now you can see, actually, this equation which I have written in determinant form in equation number 9, you can see this is an fth degree equation in En1. In terms of En1, this is an equation of degree f. And as you know, if the equation is of degree f, it will have f independent solutions. Or you can say there will be f roots of independent or different roots of this equation. And when you say that this equation will have f different roots, it means this en1 will have actually f different values. Okay. In fact, these roots are the first order correction to the energy eigenvalues En alpha, okay, of the Hamiltonian H. Now, if your aim is to find the coefficient A alpha, your aim is to find the coefficient A alpha. For this, you must simply substitute the roots of this equation, which are actually f values of En1. These roots are substituted in this equation, which I have mentioned here, in equation 8. When you will substitute the roots here, okay, one by one in this equation number 8, and then you will solve. Then after solution, the resulting expression will give you the values of the coefficient A alpha. Okay? And then you may determine the eigenfunction kth psi n, okay, of the Hamiltonian H. Then after this calculation, you may find it in zeroth approximation. But how this kth psi n will be obtained? As you can see, I have already defined this cot psi n previously here. This is the expression for kth psi n. And using this equation, after knowing the coefficient A alpha from solving that, finding the roots of that determinant and substituting that root in this equation, which I have written here, you can obtain the value of A alpha. Okay? And once this A alpha is known, then this kth psi n, which is the zeroth order eigenvector or eigenfunction, that can be determined. Okay? So this is the technique. Actually, all these facts which I have just explained, I have mentioned here for your convenience. You may note down these things in your notebook. Just I am giving the reading for more clarification. You can see this is an fth degree equation in En1, and in general it has f different real roots, En1, En2, so on, Enf. Or in brief, you can write En alpha of 1. In fact, I have written here that it has in general f different real roots. But remember, there may be, it is possible that all roots are not different. It is possible. Actually, in that case, we simply say that the degeneracy is partially lifted. If all the roots are different, then we say that the degeneracy will be lifted completely, wholly. But if the situation is such that all the roots are not completely different, then we say that the removal of the degeneracy is partial. Okay? Again, you can see these roots are the first order correction. You know, En1, En2, En1, En2, Enf1. All these are the correction in first order. All are the first order correction term in the energy eigenvalue En alpha. Okay. Now, as I have told you that for finding the coefficient A alpha, we need simply to substitute these roots into equation 8 and then solve the resulting expression. And solving it, we can find the coefficient A alpha, and after knowing the coefficient A alpha from equation 3, you can obtain the value of kth psi n. okay, in zeroth approximation. These things I have already explained. Now, as I have told you just now that the roots en alpha 1, that is en1 1, en2 1, en3 1 of this equation 9. Okay, are in general different. Okay, in this case, the eigenvalues H are not degenerate, and hence the f-fold degenerate level En0 of the unperturbed problem is split into f different levels En alpha. Okay, and where En alpha will be En0 plus En alpha 1. This is the unperturbed energy eigenvalue, and this is the correction term. Okay, so if your aim is to find En1, then this will be En0 plus En1 1. This is the correction term. Okay, and in this similar manner you can find En2, En3 and so on. So in this way the perturbation removes or lifts the degeneracy. Okay, the removal of degeneracy may be either total or partial, depending on whether all roots of 9 or only some of them are different. If all roots of equation 9, just I have told you, are different, then you simply say that corresponding to different energy eigenstate, eigenvalue, there is different eigenstate. And so that is the situation of non-degeneracy. Or in this condition we simply say that the degeneracy has been completely lifted, completely removed. But if let us consider there are 50 roots of that equation, and among those 50 roots 30 are different and 20 are equal, then the degeneracy will be lifted only partially. Okay, so in this way you can see that the degeneracy may be lifted partially or may be lifted completely. Okay, so this is the actually the basic theory for the degenerate perturbation theory. Okay, now I am just providing you a summary of this theory, and if you will follow this summary you can solve any problem based on this degenerate perturbation theory. But for that you must need the knowledge of spherical harmonics, the radial coordinate and many more. Okay. So what steps we will follow actually in applying the degenerate perturbation theory? Okay. So if let us say you have to determine the eigenvalues to first order and eigenstate to zeroth order for an n-fold degenerate level from this perturbation theory, how you will proceed, what steps you will follow. So in first step, first of all, you can see for each f-fold degenerate level we determine the f by f matrix of the perturbation HP. You have seen that this is the matrix element for the perturbation HP, which I have defined here. Okay, this is the matrix element, and this will be if alpha and beta both have values f, then this will form a f by f matrix. Okay, and this is defined as HP equal to HP11. Here actually in first term you take alpha equal to beta and both equal to 1. In second term HP12, it means alpha is 1 but beta is 2, and in this way the last element is HP1F. So these are the F elements of the first row. Similarly, you may write the second row, elements of second row and elements of the Fth row. So you can see this is actually F by F matrix, okay, for this perturbation term HP. Okay. So this will be our first step. In first step, what we will do? We will actually determine the F by F matrix of this perturbation HP. Okay. And as I have told you that how this matrix element is defined, we have already defined earlier, and you can see that this HP alpha beta in general is defined by this expression. Okay. So the value of each element of this matrix can be obtained by solving this expression. Okay, and when you will actually solve this equation, you have to write the integral form. This is integral phi n alpha beta star, okay, alpha beta star HP phi n beta and theta. Okay. So in this way you can obtain its value. Now in the second step, we actually diagonalize the matrix which I have just written earlier. Okay. And by diagonalizing that matrix, we find the values of the energy eigenvalues. You can say En alpha of 1. For alpha, as alpha has F values, so En alpha of 1, this will have F value. This will be En 1 1, okay, En 2 1, and in this way En F1. So all these F values of the energy can be found by simply diagonalizing that matrix. Okay. And when you will diagonalize it, then the corresponding eigenvectors will be also obtained, and you can see A alpha is given by this column matrix A alpha 1, A alpha 2, A alpha, and so on. Okay. Now, after these two steps, in final step we find the energy eigenvalues and the eigenvector. Energy eigenvalues and the eigenvector you can find. This En alpha will be given by En0 plus En alpha 1. This is the first order correction term. Okay. And you have already obtained the value of first order correction term by how? When you will actually solve this F by F matrix, then solving this F by F matrix, actually we obtain the value of this energy eigenvalue. Okay. And after that, finally we find the eigenvectors corresponding to that energy eigenvalue in zeroth order, and that is given by kth psi n alpha equal to summation beta 1 to f A alpha beta times kth phi n beta. Okay. So this is the basic theory. But when we will actually consider a proper application, a proper problem to illustrate this theory, then your idea will be clear. This theory is necessary to know you, particularly for writing the answer of question in your examination, particularly in university examination, when you are asked to write the degenerate perturbation theory. Okay, I explained degenerate perturbation theory, then this will be the answer. But particularly in competitive examination, some application will be asked. Okay, so when we will consider the actual physical problem and explain using this perturbation theory, then you will see what steps we have to follow for solving the problem. Okay, thank you very much.